Hello and welcome to the show. My name's Relevant. This is Do All the Things. On today's episode, a PWM controller for controlling fans, so that I can better prime on my pumps when I'm fixing on water cooling loops. So if you've been following the comedy, you know I play with the open loop water cooling there, and I recently worked on one of my computers. And one problem that I'm having is, when you're trying to prime on that pump, it goes too fast. If you got the D5 with the PWM like I do, there's no speed controller on it, so it just goes ripping as soon as you click the power on. Now, you might have heard mention of this little contraption that I built to help control the pumps. You know, we got Molex in, Molex out, and then a switch and an actual plug for a foot switch. So, while I'm manipulating the computer, I can just tappy with my toes there and get that pump flowing. But one thing that this thing's missing is some form of speed control. It does have this switch, which will output 5 volts to the 12 volt pin to, half throttle certain pumps. Some of the other style pumps that I've worked with will work that way, but the D5 won't. Neither will the DDC, if I recall correctly. Now, both the DDC pump and the D5 in my inventory are PWM. I need to find a way to control that speed, to control that PWM externally. And I was, the other day, years old, when I was sitting there like, that would be super stupid easy. Like, generating a PWM signal, all I need is the specifications. Look them up online. They're right there. And in a moment of inspiration, I came down to the shop and I just kind of sneezed this out on the breadboard, and sure enough, we got our fan here, and we give our fan a negative and we give our fan a positive, and she's ripping. And then we got the magic third pin, plug it in right there. Oh, now she's not ripping. And now if I turn on this little knob here, fan goes fast, fan goes slow. So what is PWM? Pulse width modulation. It's actually kind of silly how it works on a fundamental scale. You see, this little pin here kind of tells the fan to turn on and off. If I take the control pin, connect it directly to plus, it goes fast. Connect it directly to negative, it goes to its slowest. One might be like, oh, so what, it varies the voltage? No, it's logic. Now, let's take a look at the electrovision and see what's going on. You see, if I turn it down, this little formula here on the screen goes like that. If I turn it up, it goes like this. What you see there is a square wave, and that's the signal telling the fan to turn on and off. So basically, boom, turn it on for this long, boom, turn it off for this long, boom, turn it on for this long, and so on and so off, and so off. The fundament is, if you take a light switch and flick it on and off real quick, well, your bulb's not gonna have time to come up to speed there, up to temperature, so it runs dim. You're basically turning the fan on, and then before it can come fully up to speed, you turn it off. You keep fiddling with it like that, you keep tricking it, you keep trolling on it like that, and then it only runs half speed. Now, this is a pure square wave, which is digital, logic, and if we turn it down, you see, oh, it's turned on for less amount of time, it's turned off for more time. We throttle the speed up, it's turned on for more time, it's turned off for less time. And you see down here, we have our frequency, 24 kilohertz right now. The target frequency for PWM is around 25 kilohertz. You can go plus or minus a little bit there, which is good because our circuit's so simple, it's not 100% accurate. And then this important piece of information right there, the duty cycle, that's basically telling you the percent ratio. So if we go to say a 50% duty cycle, well, that means because it's at exactly 50% on, 50% off. Here's a 27% duty cycle, 27% on, whatever the other percent is off. Now, obviously there's more to PWM than just switching stuff on and off. Usually there's other circuitries in there that take that and stabilize and average the voltage kind of thing. It basically kind of works on a time constant. As you apply power to something, you don't go from 0 to 12 volts instantly. There's a ramp up. That ramp up might be in the nanoseconds, imperceivable to us, but there is a ramp up, and you kind of hit a target voltage, and then that's where the circuit cuts it off. So once it hits a target voltage, it turns it off. Comes up, hits a target voltage, turns it off. And then there's usually some sort of inductors and capacitors in there that take that spiky bits and smooths it out so it just becomes a constant target voltage. So the specifications, 25 kilohertz, 3 to 5 volts. So even though it's a 12 volt fan, that digital signature we're giving us, it's only the 3 to 5 volt range. Here I've established 4.5 volts. There's some losses in the circuit, 5 volt regulated circuit. I guess I should show you the schematic of how stupid simple it is. There is the gist of it, sir. We got our 12 volts coming in. We got a 4148, just a basic diode for reverse polarity protection in case I do something wrong here, but also to preserve our buffering. So we have a 220U reservoir capacitor pooling up some energy for this circuit. Probably a bit overkill. I could probably go down lower, maybe 10U, whatever, but I had a lot of 220s in stock, so I figured I'd use it for this. When it comes to capacitance, sometimes it's the more the merrier. As long as you're factoring ESR, which is not applicable to that position. Then, boom, our little 78L05 linear regulator looks like this little transistor dealie right here. Input, ground, output, 5 volts output to control our circuit. 10U reservoir capacitor after that to store up the energy. Now, these capacitors were half chosen. I did experiments. I'm like hazy on capacitor math, so I basically just experiment until it works the way I wanted to. The incorrect capacitance might result in a crash of the circuit. So I basically just messed with capacitors until I could reliably hot plug the fan without the circuit crashing. With smaller value capacitors, I'd hot plug the fan in and then boom, the circuit would glitch out and the fan would just full spin out. So we got this little pupper right here. That's the little key point here. And actually, this needs a little something else attached to it, a little like that. That is a Schmitt trigger inverter, specifically a 74HC1G14. I'm going to be talking a lot about those things on my channel. I'm not sure what order I'm posting these videos, so you might not have no context on how I got to being designing circuits like this, but Schmitt trigger inverters are so freaking handy. So basically what the Schmitt trigger does is it gives an exaggerated output based on the input. Some circuits, as the voltage goes up and down, the output might also vary. Schmitt trigger eliminates that. Once you hit a certain threshold, it just flip-flops extreme direction back and forth in the output just to get rid of any peaks and valleys. And then an inverter, well, the inverter is like the, you know, kind of troll child of the logic circuits. It does the opposite of what you tell it to do. So if you put in a positive signal, high, it'll put out a negative signal, low. If you put in a negative signal, low, it puts out a positive signal, high. The output is always active. It's either negative or positive. It either connects the output to the ground or to the positive. It's never off. So keep that in mind playing with them. So it inverts whatever signals put into it. And then here we have a feedback loop. So it keeps feedbacking on itself, and that's how we get a square wave, because it's turning itself on and off. So say it's putting out positive. That positive flows through the feedback, starts charging up this capacitor. Once it hits the upper voltage threshold, it sees a high input, it puts out a low. Through the feedback loop, that capacitor can discharge to the ground, and then once it hits the lower voltage threshold, the inverter puts out a high signal. Then through the feedback loop, that high signal charges up the capacitor, and so on and so off. And that's how we get our Schmitt trigger inverter generating that sine wave. Basically, these little guys replace the 555 timer in kind of 90% of the circuits you would use a 5.5 timer for. I have one 555 timer in inventory. I have yet to find a practical application for it that I can't do better with a Schmitt trigger inverter, so I've used a ton of Schmitt trigger inverters in circuits. Couple other capacitors here. We got this 0.1U. It is standard procedure to put one of those right across the voltage input of an IC to stabilize it. It's going to be very high ESR to filter out all little bits of noise that might screw with the inverter. Yes, inverters, when they're being used as what's called a relaxed oscillator to do something like this, they can get unstable from external noise, and we eliminate that by just put that little 0.1U there. It's a ceramic MLCC NPO COG, if I recall. And then so the feedback loop, normally you would have one resistor if you just wanted to produce a consistent output, but in this case we need to change the duty cycle, so we have a couple diodes. Now these diodes are SD103s. They're the high speed cousins of the 4148, if you will. Standard diodes don't switch fast enough to do these kinds of things. When you start getting into the multi-kilohertz, yeah, no, you need high speed buddies. These SD103s, they're what known as Schottky diodes, so they have the switching speed we need here. So for example, if we turn this potentiometer up for a high signal, for a fast signal, what happens is, so the positive comes out, diodes are one-way valves, it can't flow this way, so it flows this way. Because the potentiometer turns up, there's more resistance on this path, so this positive has a longer way to go back here to cause the feedback to switch over, and then once this goes negative, it can go take this path through this diode, but because the pot's turned up, it has a shorter path. So the output will stay low for a shorter duration of time than it will stay high, and then we get this. Consequently, yes, you turn the potentiometer down, the opposite happens by the paths dictated by the diodes, and then it goes like this. Now the timing in general is set by a combination of this potentiometer or whatever resistor we have in the feedback and this pupper right here, a capacitor. You see, this will resist the flow of current so that it, it can only get from point A to point B in a certain time, but this simultaneously puts a load here. If there was no load, this resistor wouldn't throttle the current, it would just flow super fast anyway, because the current is actually filling this capacitor and discharging this capacitor. So the size of this capacitor will dictate how long it takes to fill it, how long it takes to discharge it. In this case, because this potentiometer is a bit large for the application, we're using a 0.001U, aka 1N, aka 1000P capacitor to do this job. Changing this capacitor would change the frequency of our PWM. So would this pot, but 100K was chosen because it's what I had in stock. I had this one oddball pot in stock that's perfect for the application, so I decided to build the circuit around it. And then of course, shared with this output, it's just the PWM. This puts out a logic level output. This takes a logic level input. We don't really need any other buffering. An electrical engineer might tell you otherwise. There's probably some good form we could do between these 2 points. But in this case, Schmitt trigger inverters are used as buffers. They're used often in between a point A and a point B. So it works either way. And it might look tricky to some people, but this is the simplest circuit. And in fact, if we were using a Molex like this, we wouldn't even need the regulator because we have a 5-volt tap on the Molex. I'm doing that for the reason that this thing I'm building, I want it to be able to take a 12-volt only power supply to simplify things, so I've added regulation. So to show you this componentry, this is the package I normally work with. That little guy right there, 74HG114, Schmitt trigger inverter. 74 means it's logic. Most logic starts with 74. HC is the logic family, high-speed CMOS, also high current. The HC can handle up to 20 milliamps output, which is a lot for a logic circuit. 1G means it's one element. There's only one inverter on this chip. 14 is what it is, a Schmitt trigger inverter. You can get 74 HC14s, I do believe, that would have 6 elements. There's 2G14s with 2 elements. I keep those in stock too. And 3G14s with 3 elements. I have a few of those. Nothing really in between because you go just up to 6 at that point. So I do believe this is something like one of these on semis. I might have gotten it from Mauser or DigiKey at any one point, and they come in different sizes, so you got to watch out. I do believe this is the TSOP 5 package. There's one, there's one, and a TSOP 5 gets mounted on a BOB 00717 adapter, and to do that you need some Rosman schmoo, like some chip quick. I'm using NC91191. You need flux. You got to schmoo it down with flux, a fine tip soldering iron, and just some solder, and get her on there, and then I pin it up. You got to install the pins yourself, and I have a pinning jig, and it's a whole thing. In this particular guy, I'm using this other one. It's the same chip, but on a smaller package, and I can't exactly, I found the adapter. It's a 3306. A 70-6 adapter for these formats, SOT363, SC70, SC88. I don't see any part numbers on the Mauser site that match that. Oh, look, DigiKey finally has some of these in stock. These things have actually been affected by the chip shortage, and I haven't found any in stock lately. It might be the TSSOP. Oh, there's an SC88, SC7. That must be the ones that I got there. Yeah, hell yeah, 2085 in stock. This is very hard to install by hand because of how tiny it is. This is one of the first 1G14 inverters that I purchased, and for some reason I kind of messed up the sizing. I didn't realize what I was getting, and then I needed this special adapter for it. This is the one and only I have, but it's, you know what? It's been a nuisance, and finally I found a use for it. So it's gonna make it into this circuit. So I am going to modify on my control box. We have a momentary push button here that is broken. So I'm gonna replace that with this potentiometer so I can have my PWM control. And I've never really showed you the inside of this thing before. It's basically just a Mosfet relay. So in here is an IFR or IRF 1404. It's something stupid like 100 amp relays. So this thing can handle whatever current I'm gonna be pumping through these connections. And MOSFETs are great because they're so fast switching and so low impedance. Your circuit essentially sees them as a piece of wire once you turn them on. A quick rundown of what's going on with that. It's very simple using a MOSFET as a switch. This is an N-channel MOSFET. We have our positive line, we have our negative line. N-channel MOSFETs switch negative and they're controlled by positive. The input on a MOSFET is active. You can't just put nothing to it. You have to tell the MOSFET what's to do. When you ground out that input, say through this 10K resistor, it turns it off, and then when you flick the switch, it turns it on. So when we flick this switch, it overcomes whatever current's coming off that 10K, and that 10K also means we're not gonna get a dead short circuit. This will see positive, this will turn on, and it'll switch our negative, which is convenient in a Molex form factor because we have both 5 and 12 volt rails. So instead of having two individual switches on the positive, we can just have a common negative switch and then boom, good to go. And here our power comes in to this switch here, and that's what selects between 12 and 5 volts to the 12 volt rail output so I can throttle speeds and stuff. I've got this weird random plastic screwy shroud so I can't accidentally flick it, and then a red LED pops up when it's in 5 volt mode to warn me it's in 5 volt mode. And boom, just this switch and this Footswitch jack connected in parallel to drive the MOSFET. So to build this, I came up with like a little PCB, I know it's not B, a little circuit layout. It's gonna go on this little piece of perf board here. There's the potentiometer, there's the diodes. These ominous 6 dots represent that Schmitt trigger inverter assembly that I have. There's our timing capacitor, there's our 0.1U, there's our regulator, input diode, input capacitor, output capacitor, crammed it all onto a very small package. And now I'm gonna build on it. Be right back. All right, here it is. Yeah. That's mounted on the other side, by the way. It's just a case of testing on it now. Let's shift the power rails over to the actual power distribution block here, sir. Then we're gonna have our 12 volt out to the fan. Then we plug these power connections to here. Now hopefully when I apply power, there's gonna be no smoke. That said, this little thing coming off here should be our PWM signal. Oh yeah. There it goes. It works. I love it when a plan comes together. It's so simple though. How can you mess this up? Usually it's the much bigger, more complicated, more ambitious circuits that I mess up. You know what I'm saying? So we have some sort of output connection here, switched plus in here. We're gonna have a fan header coming out of this thing now, so we have a little bit of a pass through. So we gotta go and get that all installed into here. And in order to do that, we're gonna have to do some reworking of the circuit. As an example, this LED is gonna be coming out. I'm just gonna go ahead and clip this wire, unsolder from the switch. This is one of those ultra bright LEDs, just what I had in stock. I'm gonna put an actual like indicator LED in there. This little push button comes out, and of course I bust this all together like cute like. Let's get that off of there. Not gonna need as much length, so we'll chop a chop. There we go. And then I don't think we're gonna need what's coming off the switch here, so we'll choppy chop that. Now, if I did my sizing correctly, it's not gonna go that way. We need to do some trimming on this actually. Oh, I've just thought that these cutters work good. I don't know if we need to trim that side yet. We do need to trim this side though. Just like that. So this guy is intended to fit Like this? Yeah. Huh. Yeah, pretty much I got my dimensions correct. That's gonna be good. Let's remove this. Slot in there like that. It'll be a lot cleaner. Oh, it kind of rubs up against the switch there. That's okay though, that's okay. You could do some very subtle modifications to remedy that. Yeah, that's gonna fit in there perfect now, bud. Pretty much. Replacing that switch, that button with a pot. Okay, now one problem we have here is the Mosfet. I need to cut off this plastic sheathing to get at the connections. This is before I started working with perf boards. It's okay though, this is a perfectly valid way to do this kind of thing. I guess we're gonna have to disconnect this wire here so that I can slide a new cover on this. Looks like I used a 15K resistor, pretty standard. This PID's folded up, that's output. So the little flange here is the output. So we need a new piece of wire from that. I'm putting this circuit post switch, so it's gonna turn on and off with the switch. That way we don't have to worry about anything I plug into it, potentially trying to pull power from it. And then I need to add a new black line here. I'm gonna go with a different color. I already got two black lines coming out of here. Let's go blue. So we're simply gonna attach another wire to the flange of this Mosfet, which actually requires a fair amount of heat, a little bit more than this fine tip will use. There we go. Gonna cut it about the same length as these other wires. Well, no, I need it to just reach over to about here. So we have everything we need from this. We can put some fresh heat shrink on it. Sparker's broken on my torch, and I have a dead lighter. Uh-oh. No, I just realized I'm not done in here, bud. Okay, yeah. Wasted a perfectly good piece of heat shrink. You see, I'm going to have an alternative power source for this thing moving forward, which means I need to tack another power input into it. White will be the new power input line. It's just got to parallel with these Molex, so like, don't accidentally plug the alternative power and the Molex in at the same time. It's funny, I'd do this very differently today. I'd probably consolidate this all into one PCB assembly. That is a chunky boy right there. This one doesn't have to be as long. All right, let's get that chunker sealed back over. Now we should be good to wrap the Mosfet. All right, now we're back from whence we came. I'm gonna remove this grommet du fromage because I've actually since acquired proper LED holders. Coincidentally, the hole seems to be about the right size. Right, this grommet is going to make a new home on the side here because here I need to punch some new holes. We'll go run right about here. Just gonna straight up slap chop these with a hand drill. Nice. I gotta put another one right about here. We're gonna put in a DC barrel jack assembly. I think I used a bit too big. A little sloppy, but it's gonna work, bud. Oh yeah, I made that hole just a touch too big. Just a touch too big. If I line it up well, it's not gonna be a problem. I remember now, it's the smaller cone bit that fits this. The different cone bits have different sizes. Now hopefully, that still fits. Yeah, okay. Now to wire this all up. So we're gonna get the red wire onto this barrel jack. Then the white is the new power input. Oh, we definitely didn't need that much length. Or the new negative input going to the Mosfet. Now this red line is going to attach to the 12 volt input on the switch, which has got a lot going on already. Look at all this crap. We're basically just jimmy rigging it now, kind of working around the sloppiness of the past, working with all these improvised components. So here is our new red LED. Here's our LED ground line of exaggerated length. And onto this switch, the 1K resistor to signify when the 5 volt system is active, assuming we're running Molex. Now that connection was floating before, I guess it could be floating again. Make sure it's not touching anything. It's not gonna really move. I might stick some glue on it after. All right, reinstall our trigger line to the button. And we're gonna reinstall our trigger lines to the Footswitch jack, bud. So this should function the way it did before. Oh, the saddest part of sacrificing on a cable. Here's one that's only gonna be a half a sacrifice. It's a PWM splitter, so it splits to 2 fans, which is something that could very much come in handy, but I'm often in the habit of marrying fans. So I could probably do without it. Yeah, chopsky. Really close to the connector. Okay, now it becomes a very short extension. And it still has some nice sleeving and heat shrink on it. Gonna take the grommet we took out of the LED hole, put it into here, and see if we can't get this through that hole. Ugh, come on now. Ugh, okay. Probably helps if we shrink on this a bit better. Yes, here we go. So now we gotta get these connections onto the little board. Blue is the PWM out. Probably gonna need the vise for this. Getting tricky now, it's all very congested here. All right. Blue is the new switched output, and that's going to combine with this black up here in the negative bus area. And this yellow is to positive. I'm positive about that. And that's going to combine with this red here. That should be all officially wired up now. Now we just have to mount this thing. Oh, it has the little nubbin, the anti-rotational nubbin. You know, I'll take a file real quick to accommodate that nubbin. So yeah, all the pots have these little sticky outy bit anti-rotational tab. I just carved a little key in there. Now that'll sit in there nice. Now where's the hardware? We have a lock nut. I guess that goes in the backside. Wait, that lock nut interferes with the anti-rotation nub. Okay, I guess this lock washer goes on this side. Let's gently snug it up. Ah, looking good, bud. Okay, I gotta kind of put it all together here. This thing needs to pull through. Like, there should be enough room for all this to pack together. It's intended that the Mosfet slips up there. And this guy is just a little bit, congested here. It doesn't, because of the location of the PWM, it does not bend nice, but we can make it happen. Okay, this could be slightly better, more ergonomically designed. Seems it partially entails most of this guy coming out the hole. Okay, let's slap a couple screws at it real quick just to secure it. Now let's see if we can't make this nice again. Get this grommet back through this hole. All right, good enough. I do believe this thing is done. If we plug in power here, it shouldn't explode. If we plug in fan, it shouldn't turn on until I press the button. There it goes, and yeah! PWM control. Off, on, off, on. And see, it gets better. This is the Footswitch assembly for it. So now I can kind of set my speed here. And then when I want to, right? That goes on the floor and we just do one of these. And just to confirm, here's the power supply that I keep handy. Unplug the barrel or else we're gonna have a bad day. This is high power, 480 watts, but it's light as frig, bud. This thing's ridiculous. I've never used it as a serious computer power supply. It's just always sat on my bench for applications like this. You got a little jumper between ground and the green pin, so that when I plug this thing in and turn it on, it just works. Then we can Molex in here, and then now this should work again. Yup. And then as mentioned, we're gonna just turn this up all the way so it's full on. Now it's full on. I have a 5-volt mode, or I used to have a 5-volt mode. Oh. Okay, yeah, the way I wired this up, that PWM output is permanently, this is on the 12-volt rail, so I can't switch to 5 volts with this connector. Maybe I should have connected this to the switch output so I could have that functionality. But you know what? It's not a deal breaker. We'll never mind that. The intended functionality of this is that if we have this like fan adapter and we're running it off the Molex, so it's running full on, still has this functionality. We flick it up to 5 volts and you see now it's half speed. So some stuff will run off Molex half speed. Light warns me it's in 5-volt mode. But we don't have that functionality on this, and that's fine. We use this to control pumps and fans that have PWM, so we're not really worried about derpy friggin' 5-volt mode. That's great. This went better and smoother than I expected. It's just, you're scratching your head one day with a problem to solve, and you're just like, wait, that solution's so easy. Let's just friggin' do it, bud. Just like friggin' hammer it out, bud. Just like, and now it's done. And next time I'm priming on my computer with my PWM pump, bud, I'm gonna have speed control over it. Oh yeah, oh yeah. And I don't even have to bust this out anymore. I can just get a barrel jack here. So that makes it even easier. And I have up to 3 and 4 amp adapters for this, so I think this one right here is actually, it's only 1.5. I don't know if that's enough for a D5. D5s are a little thirsty, but we're gonna find out. Either way, we're done here. Another successful project. Now, mind you, I've said that before and had my circuits fail, so there's follow-up videos to some things. Yeah, if you enjoyed this, stay tuned for more, because I like doing stuff like this sometimes. Oh yeah, That's great. 2.0. Yeah. Turn off you.